Hey y'all, it's Mr. Boyden, your personal math teacher, back at it again, and today we continue getting into some real inference in our statistics course by talking about some confidence intervals, which is our first example of an interval estimate. To do this, let's jump right into an example, and by the way, today's lesson, we're not going to be doing a whole lot of calculations. This video is going to be focused on understanding the concept of what a confidence interval is, and then in a later video, we're going to learn how they're calculated, both for proportions and for means. So let's get into the concept now. Okay, here's our example. Let's say that we've taken a sample of students and we ask them if they have a pet at home. And we find that p hat is 0.63, so keep in mind that 63% of students have a pet at home. That's the sample proportion. And we know that p hat is an unbiased estimator, so we know the statistic isn't biased, but how do we know how accurate it is estimating p? Remember, that's the purpose of doing sampling. We're trying to estimate what the proportion would be for all students, and that's why you would do a sample. So we say in our sample, we got 63% had pets. What does that tell us about if we had asked all students? What kind of estimation can we make? So we have a new term down here, and that's point estimate. P hat is a point estimate because it's only one value. It's not a range of values. If it were a range of values, it would be called an interval estimate. And a confidence interval is the most common form that we have of an interval estimate. And it's really the only one that we're going to use in this course. To help you understand what that is, we're going to try to answer these questions below, keeping in mind that p hat was 0.63. All right, so here are the questions. You may want to pause the video now and try to think about what your answers to these questions would be. How confident are we that the proportion of all students who have a pet is between 0.62 and 0.64? We know that our sample said it would be, our sample returned a value of 63% or 0.63, but does that mean for sure that if we had asked every student in the school, that number would have landed between 0.62 and 0.64? Not really. We're not really, I want you to say not very, and I'd like you to try to say basically like what percentage sure are you? Are you 20% sure that it would be in there? Are you 5% sure? I'm going to make a guess, like, I don't know, 15% sure? Not very sure. It actually seems, I mean, yeah, I wouldn't bet on that. I wouldn't put money down. Let's expand the range out a little bit in question 2 though. How confident are you that the proportion of all students who have a pet in the school is between 60% and 66%? All right, that's a little bit wider interval. And so it's more likely that, as compared to the first interval, that the true proportion for all students would be in there. So I don't know, maybe we're up to like 40% sure by now? Next question, how confident are we that the true proportion of all students who have a pet is between 43 and 83%? Okay, that's a big window. And because that's such a big window, it's pretty likely that the true proportion is going to be in there. So I'm going to go, I don't know, 90% sure. Now it's possible, maybe 90% of students have pets, and in our sample, we just happen to get a higher proportion of students who don't have a pet. But it seems like that's a pretty big window, and so it would be likely. Okay, these are all examples of confidence intervals. Okay, so one thing I want you to notice about them is they are all symmetrical about the point estimate. So notice, like, this interval was constructed by taking 0.63 and adding 0.01 to the right and subtracting 0.01 to the left. The next one by taking 0.63 and adding 0.03. So I'm going to write it as plus or minus 0.03 on either side. And this last one was constructed by taking 0.63 and adding or subtracting 0.2 or 20% on each side. And there's some key concepts that we need to understand that are illustrated in this example. The broader the interval, the more sure we can be that the true proportion or the true mean, depending on what we measured, we can be more sure that that number is going to be in there. And if that's not clear yet, let me give you a crazy example. How sure would we be that the true proportion of students who have a pet lies between 0 and 100%? Well, there's nowhere else it could lie. We would be 100% sure that the truth lies in there. And so that broad interval, if it gets really broad, then we become totally sure. But then it's not useful. Like saying, you've probably heard people say something like, I'm 100% sure that it will or won't rain. It's like, well, yeah, I mean, you've included all possibilities. We have all possibilities in this range, so it's not very helpful. Versus if we get really specific, then we can't be as sure. That would be like me saying, me making a prediction, like I think that we're going to hit a 3-pointer in the 3rd minute of the basketball game. That's really specific, and because it's so specific, it's not that likely to happen. But if I made a more general, a more wide open claim, like I think that at some point this season, our basketball team will hit a 3-point shot. Well, now that I've opened that range of possibilities way up, that's very likely to happen. So we'd be much more confident that that would happen. Okay, and so this is a way of estimating. And sometimes you'll hear something like that. Like the confidence interval goes from this, we are whatever percent sure, 40% wouldn't be very good. But if someone said we were 95% sure that the true proportion lies in there, you'd say, okay, cool. That feels like that's a pretty useful piece of information. Okay, so that's the example. Now we're going to get just a little bit more into the specifics and some vocab. Okay, so we already said that we're going to have confidence intervals. And the reason we use confidence intervals, this is something that a lot of students get lost on. Like, why do we even need that? Like, we can just take a good sample and just call it good. No, we can't. Because even though we do perfect sampling methodology, even though we randomize and we use a good sample method, like any of the ones that we've already learned, you're still going to have a margin of error because of sampling variability, right? We know that in the sampling distribution, you're going to get one of those values for your point estimate, for your p hat or x bar. And so we recognize, like, wait, that's not necessarily the exact proportion of the population that would say yes to this question or whatever it is. And so that's why we need a confidence interval to say, hey, we're not sure, but we're pretty sure it's in this range. So in the example we had a moment ago, p hat was 0.63. If the margin of error was 0.08, what that means is that we would add and subtract 0.08 on either side of that interval. And so our confidence interval would go from 0.55 up to 0.71. Now, this right here, we're using interval notation. This goes back to like pre-calculus. Okay, so that's a common way that it's expressed. What I have right below that here, in general, this is how confidence intervals are calculated. We start with our point estimate. I'm going to add a little something to that because point estimate's a new vocab term. The point estimate is always a statistic. And in this class, it's typically p hat or x bar. And then we add and subtract the margin of error to that on either side. Okay, we're going to learn more in a later video about how the margin of error is calculated. For today, take it at face value. Okay, the margin of error is related to the confidence level and the sample size. Okay, that was something we didn't talk about quite yet, is the sample size. The confidence level is referred to by a capital letter C, and what it's meant to tell us, at least, is the success rate of the interval capturing the true population proportion, or the true mean. We're going to do a visual of that in just a second. So another way of thinking about this is like if you took all the possible samples from the population, the sampling distribution is what that's referring to, the confidence intervals of C% of them would actually contain the population proportion. Let's switch over real quick and actually look at a visual of what that would mean. Okay, we're going to run a simulation over here. And what this is going to do, when I click this button, it's going to take a sample of size 25 from a normal population. And it's going to construct confidence intervals based on the means or proportions that it records. I forget if this one records means or proportions. Let's see. So let's do a sample. And so what we have here in each of these bubbles, so notice, let's look at this red one, for example. You see how we have that red dot in the middle? That's the point estimate. And then it's adding the margin of error to go to the right. That's what this wing on the right is about. And then it's subtracting the margin of error to go left. And so based on the data points, so this is sampling variability, right? Based on this was the sample, they had that mean value, and then they constructed the confidence interval. We have to understand that sometimes the true mean, which is represented by this green bar, is not actually inside of that interval. Why? Because in order to guarantee that it would always be inside of there, we'd have to construct a 100% confidence interval. Remember, the more specific the claim, the less likely it is to actually happen. That's essentially what's happening here. But look at all these other point estimates and their confidence intervals. They're in black or gray, whatever that color is, if the true mean, mu, seen at the top of the screen, is within that interval. And so for all of those it is. Now notice over here on the left, it was in the interval 92% of the time for this one. So let's do another sample. 92 again, that means 2 of them were misses. Let's do it again. Ooh, 3 of them were misses this time. That's interesting. Okay, and then 2 of them. Now, why is that? So our confidence level is 95%. That's actually really surprising. Interesting. So I guess you can see right now, I don't rig this. We did this in class the other day. We were getting a lot of 96s. So let's play with this a little bit. Let's lower the confidence level and see how that changes how many of our intervals capture the true mean. So look at that. So now we have a bunch more in red, and still a few, and now a bunch more. Did you notice how the intervals changed as I moved this slider up and down? So notice, if I make a a prediction that I'm very sure about, 99.5% sure, these intervals have to get wider so that it's more likely that the mean will be within those ranges. Versus if I go down and my confidence level is lower, that's almost like making a more specific prediction. That's like saying, hey, I think we're going to hit a 3-pointer in the next minute. And so that's less likely than saying, hey, I think we're going to hit a 3-pointer at some point in this game. Okay. What about sample size? How does that affect it? So notice, with a big sample size, I'm getting these smaller little intervals. Even if I bring my confidence level up, I still get relatively small intervals. Now, why is that? We saw in Unit 7 that when we have a larger sample size, the standard deviation of the sampling distribution decreases. That's one of the factors in creating a confidence interval. So with a higher sample size, we get closer and closer to the truth of whatever parameter we're trying to estimate. Okay, so that's why that's happening. So with that in mind, let's come down and try to answer these questions. So how does changing C influence our confidence intervals? You may want to take time to write this if you're someone who's taking notes right now. Okay, so how does changing C influence our confidence intervals? Well, we saw that as the confidence level goes up, the intervals get wider. And as the confidence level goes down, they get narrower. Okay. What about sample size? I guess I missed that question. How does the sample size influence our confidence intervals? Bigger sample size means the interval gets smaller, because the bigger sample size we have, the more we can feel like we're closing in on the truth. If that sounds weird to you, think about it like this. Imagine a question where we were going to ask people how many siblings they have. If you ask only one person and that person says, I have 7 siblings, would you assume that that's the mean for the population, that on average people have 7 siblings? Probably not. If you asked 4,000 people and the average of the 4,000 people you asked was 3, would you assume that you're closer to the truth than if you'd only asked one person? Of course. If we ask lots and lots and lots of people, we have more information, we can feel like we're starting to zero in on the true proportion or the true mean. And that's why that works that way. Okay. Just so you know, in this in an AP class, and largely in science as well, in most areas of science, the most common confidence level is 95%, although in some fields I have heard that 80%, 98%, and 99% are used sometimes. All right, next thing here. For an AP exam, there are common questions and we need to know how to answer them. And it's kind of like when asked about to interpret the standard deviation, same thing here. There's a specific answer they're looking for. They're like with a standard deviation, they're asking about the typical distance from the mean. Okay, so I want to encourage you, if you're taking the AP exam this year, that you would pause your video right here and probably write these down. Okay, and if not, then maybe you continue on just watching the video as is. But if on an AP exam, if they asked us to interpret the confidence interval, we're going to say that we are C% confident that the interval from whatever the 2 values were captures state the parameter. And what that means, you might say like the true proportion of people at our school who have a pet. So you would restate the parameter in the population. That's a different question than if you're asked to interpret the confidence level, where they say if we select many random samples from a population and construct C% confidence interval using each sample, then about that percent of intervals would capture the true proportion of students at our school who have a pet. Let's try an example. What I'd like to do is give you an opportunity to pause the video and try this for yourself and then check and see how you did. Here's a question. The Pew Research Center and Smithsonian Magazine recently quizzed a random sample of 1,006 U.S. adults on their knowledge of science. One of the questions asked them, which gas makes up most of the Earth's atmosphere? Is it hydrogen, nitrogen, carbon dioxide, or oxygen? Then they had a 95% confidence interval from the proportion who would correctly answer nitrogen, and that was 0.175 to 0.225. As you're going through this question, if you're getting thrown off by the fact that those are decimals, you could choose to rewrite them. And don't write it in your answer, but just on the side for yourself. You could write those out as 17.5%. Oops, 17.5% and 22.5%. And we're asked 3 questions. Interpret the confidence interval. That's a total canned response. It's fill in the blanks. So we'll talk about that in a second. They ask us to calculate the point estimate and the margin of error. And the third one is, they ask us, if we guess one of the 4 choices at random, then about 25% should get the answer correct. Does the interval that was given provide convincing evidence that less than 25% of all adults would answer this question correctly? Okay, so what we're going to do here, I'm actually going to talk about 2 and 3 first because they may require some explanation. 1, we're just going to check the answer after this. But let's actually talk through 2 and 3. A lot of times people get stuck on what the point estimate would be and the margin of error. But what you need to remember is that the point estimate is always halfway in between the 2 ends of the interval. We saw that visually when we had like the circle and the little bars. These 2 bars are the same length, or if I wanted to mark them up like it's geometry, we'd mark them like that. And what that means is the endpoint on this one of the endpoints is at 17.5, the other endpoint is at 22.5. So we just need to figure out what number's in the middle of that. It will always work to just find the average of those. So 0.175 plus 0.225, divide it by 2, and you get 0.2, or if you wanted to, you could interpret that as the point estimate was 20%. In layman's terms, that means that when they conducted this survey, 20% of the people answered correctly. So 0.2. And the margin of error, that's this distance out here and that distance out there. So how far is that? We can probably tell by just looking on this one. Okay, that's 2. So MOE is what I'm going to call margin of error. The margin of error, if we think about it in percentage, it's 2.5%. However, we want to answer as a proportion. So we're going to say 0.025. So that's the point estimate right there. The point estimate, and specifically it's a p-hat value. And then the margin of error is just how far to the right and left did they go to make those intervals. Now, question 3. I want you to think about this more as like a question where it asks, is it surprise, or would it be surprising if 25% of people answered it correctly? Because that's a type of question we've had a lot. And we have to think about what the confidence interval means. At a confidence level of 95%, we are 95% sure, let's do it on a number line. So if this is 25%, we are 95% sure that the true proportion of U.S. adults who would answer this question correctly is somewhere in this red bar. So if you asked all the adults, we are 95% sure it would land up in there. And that's 0.175 and 0.225. And so when this question asks you, do you have convincing evidence that less than 25% of U.S. adults would answer correctly? So basically, do you feel really strongly that the true proportion is less than 0.25? Heck yes. We're 95% sure that it's in this range. And really what we're looking for, this range does not overlap, not even close, with 0.25. So yes, that is convincing evidence. Absolutely. Okay, and then what about number 1? I'm just going to go ahead and put that on the screen here. So there it is. We are 95% confident that the interval from 0.175 to 0.225 captures the true proportion of U.S. adults who would answer correctly, or who would correctly answer. Okay. If you're 1 or 2 words off, you're not going to get marked down on those on the AP exam, but you do need to capture that golden answer, or that golden response that I kind of showed you up above. Okay. Let's do another example, because it seems like with examples we gain more understanding. Let's do another one. And here it is. Once again, I want to invite you to pause the video and give it a try, and then hit play when you're ready to go through it. Here it is. As part of a school project about response bias, Ellery surveys a random sample of 25 students from her school. One of the questions in the survey required students to state their GPA aloud. Scary. Based on the responses, Ellery said she was 95% confident that the interval from 3.14 to 3.52 captures the mean GPA for all students at her school. We'll interpret the confidence level in just a minute. Let's answer B and C first, just like the previous question. We need to first explain what would happen to the length of the interval if the confidence level were increased to 99%. So remember, with an increasing confidence level, we have to increase the width of our interval so that we are basically upping the likelihood of capturing the true mean in this case. Okay, so it would get wider. Another way of saying that is that the margin of error would increase. In our next video, we'll learn how to calculate the margin of error, but we can already see that the confidence level is part of that calculation. What about part C? How would a 90% confidence interval on a sample size of 200 compared to the original? So we're talking about a bigger sample. So we're going from 25 students to 200 students. Well, remember, the more data you take, the more you start to zero in on the true parameter. In this case, it's the mean. So we would expect the interval will narrow. Okay, and rather than having you watch me write this whole answer out for A, let's just go look for it over here. Okay, and there it is. If we make many 90% confidence intervals, about 90% will capture the true mean. This actually is not a great response. It's if we take many samples and construct 90% confidence intervals for each one, about 90% will capture the true mean. You're not just making them. So if we make 90% confidence intervals from many samples, that's how I can salvage this answer. It says from a curriculum place I got this. Okay, so now that's an acceptable answer. People, that's your basic intro to confidence intervals. I hope that's helpful. I hope you enjoyed this one, and I hope this will be a really good lead into the next couple of videos that are coming out soon. And so until then, I'll see you next time.